This problem asks, what is the net force on Q2? This seems simple and straightforward, but because our arrangement is in two dimensions, it's going to be a little bit trickier than maybe first thought. So it's asking for force, so it's always good to start by drawing a free body diagram. And here our charge Q2 is interacting with two other charges. So Q2 and Q1 both have the same sign charge, so they're going to feel a repulsive force. So this is the force on 2 due to 1. And Q2 and Q3 have opposite charges. They'll feel an attractive force. So this is going to be the force on 2 due to 3. Now we can assume these are all point charges, and we can use Coulombs Law to model the forces on them. We also know that for Coulombs Law we need the size of the charges, which we have, but we also need the distance between the charges. We have the distance between Q2 and Q3, but we don't have it for Q2 and Q1. So that distance is going to be this distance right here. But if we notice, this makes that's the hypotenuse of a right triangle with sides of 3 and 5. So the distance we're looking for here is just going to be the square root of 5 squared plus 3 squared, which is about 5.8 centimeters. Now that we have all the distances, we can use Coulombs Law to find the size of these two forces. So the force on 2 due to 1 is going to just simply be K times Q2, which is 1 Coulomb, times Q1, which is 3 coulombs, divided by the distance between them, 5.8 centimeters squared. And actually, let's use the meter version of this, since meters are part of our K constant. So this is 0.058 meters squared. And this gives you about 8 times 10 to the 12th newtons. The same thing for the force on 2 due to 3. K times 1 coulomb times 2 coulombs divided by 0.03 meters squared. And this turns out to be about 20 times 10 to the 12th newtons. So if we look at our free body diagram again, our force on 2 due to 3 is okay because it's in the negative y direction, but our other force is at an angle, so I'm going to redraw this force a little bit bigger. Here's F21. We're going to have to break into components to solve this, so this is F21y. This I'll call F21x. Now, if we want to figure out how big these are, we could find our angle theta here in our problem, because the angle of our distance triangle is actually the same as the angular force triangle. So you could find that using like inverse tangent, for example. And then again, F21y is going to be F21 cosine theta. F21x would be F21 sine theta. But remember, sine and cosine are really just ratios of sides of a triangle. We have all the sides of this distance triangle, 5, 3, and 5.8. So we could also write sine and cosine that way. I'm going to do that to make our life a little bit easier. So F21y is going to be F21, which is 8 times 10 to the 12th. Now, according to our picture here, cosine of theta would be if theta is down here, would be the adjacent side over the hypotenuse. So this is going to be, actually I just realized I wrote these backwards. That's sine and this one's cosine. So sine theta is opposite over hypotenuse, so it's really just 3 over 5.8. So F21y is going to be about 4.1 times 10 to the 12 newtons. F21x, again, we do the same thing. This is 8 times 10 to the 12th. Cosine of our angle is going to be the ratio of 5 over 5.8, which is the adjacent side divided by hypotenuse. And that gives us that F21x is going to be about 6.9 times 10 to the 12th newtons. A couple steps left. We can now write our sum of the forces equations. Sum of the force in the x direction is just F21x, which is 6.9 times 10 to the 12th newtons. Sum of the force in the y, F21y minus F23. So that's going to be 4.1 times 10 to the 12th minus 20 times 10 to the 12th, which gives us about negative 1.6 times 10 to the 13th, or actually let's write it as times 10 to the 12th to be consistent, so negative 16 times 10 to the 12 newtons. So all we have to do now is put together our sum of the forces in each direction. So here's sum of the forces in the x, sum of the forces in the y. This one's be consistent, should be a little bit bigger. So we want to find the total sum of the force on this and the angle it's acting at. So the total sum of the force, switch colors, is just going to be the square root of 6.9 times 10 to the 12th squared plus 16 times 10 to the 12th squared, which gives us a total force of about 17.4 times 20 to the 12 newtons. There's the magnitude of my net force, and the angle that it acts at, I can use inverse tangent. Is going to be the inverse tangent of 16 over 6.9, which is about 67 degrees.